Welcome to this course on aromaticity. Aromaticity is a property of conjugated cycloalkenes in which the stabilization of the molecule is enhanced due to the ability of the electrons in the pi orbitals to delocalize. This acts as a framework to create a planar molecule. When we say aromatic, the first thought that comes into our mind is aroma, smell. We always think that those compounds which has a smell or aroma is aromatic. But do all compounds with a smell are aromatic? It's $1 million question. Many aliphatic esters have smell, but they are not aromatic. But why do we care if a compound is aromatic or not? Because we encounter aromatics every day of our lives. Without aromatic compounds, we would not only be lacking many material necessities, our bodies would also not be able to function. Aromatic compounds are essential in many industries, including pharmaceuticals. Around 40 million tons of aromatic compounds are produced in the world every year to produce important chemicals and polymers such as polyester and nylon. Aromatic compounds are also vital to the biochemistry of all living things. 3 of the 20 amino acids that are used to form proteins, which are the building blocks of life, are aromatic compounds. And all 5 of the nucleotides that make up DNA and RNA sequences are all aromatic compounds. Therefore, we can say that aromatic compounds are vital to us in many aspects. Let us move into some historical facts that leads to our discussion today. It started with Michael Faraday in 1825 when he isolated a new hydrocarbon from illuminating gas. Later, it was followed by Hilhard Mitschkrieg in 1834, who isolated the same substance and determines its empirical formula to be CnHn, and the compound was named benzene. Later in 1845, August W. von Hofmann isolated benzene from coal tar. And in 1866, Auguste Kekule proposed a structure for benzene. In order to understand the aromaticity and its principles, we need to first understand the basic concept of electron delocalization and resonance. When we talk about aromaticity, the first compound that comes into our mind is benzene. Benzene was first isolated by Michael Faraday in 1825, which is the simplest and ideal molecule to illustrate electron delocalization, resonance, and aromaticity. Here are some of the important milestones during the structural elucidation of benzene. Frederick Kekule in 1866 proposed an equilibrating cyclic structure for benzene, which partially explained the existence of 3 isomers instead of 4 for a disubstituted benzene. If benzene is just a cyclotriene, replacement of 2 hydrogen atoms in benzene by 2 bromine in principle should give 4 compounds. In reality, we get only 3 corresponding to 1, 2, 1, 3 and 1, 4 substitutions. Kekule assumed that the two 1, 2 disubstituted benzenes interconvert too rapidly to be distinguished, and therefore there is no individual existence for the 1, 2 disubstituted benzene. In 1901, hydrogenation of benzene to cyclohexane by Paul Sabatier confirmed its cyclic structure. This added more proof to the existence of benzene. But there has always been much debate over the structure of benzene. But all these debate came to an end in 1930s when X-ray and electron diffraction studies confirmed that it is planar, regular hexagon in which all the carbon-carbon bond lengths are 1.39 angstrom unit, which is shorter than the carbon-carbon single bond, which is 1.54 angstrom unit, but slightly longer than the carbon-carbon double bond, which is 1.33 angstrom unit. Now such a structure is possible only if all the carbon atoms have the same electron density with sufficient pi electron delocalization over the entire skeleton ring of carbon. Now we know that all carbon atom in benzene are sp2 hybridized, and each carbon atom uses two of these hybridized orbitals to form 2 sigma bonds with neighboring carbon atom and use the third orbital to form a sigma bond with 1s orbital of hydrogen. In addition, each carbon atom has a p orbital right angle to the sp2 hybridized orbital, and the planarity of the molecule allows these orbitals to overlap sideways, leading to delocalization. It is now clear that benzene does not contain any double bond, and the exact structure is the resonance hybrid of a two possible Kekule structure with delocalized electrons. Now, in this contributing structures, the contributing structures or resonance structures are shown with double-headed arrows separating them. This does not mean that these two structures are in equilibrium with one another, but it only tells us that the actual structure lies somewhere in between these two contributing forms. So let us not mistake that these two are equilibrating structures.